Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Welcome back another session of Artificial Intelligence. In this session, we are going to learn about a single layer feed-forward networks. So, in the previous session, we have already started artificial neural networks. In that, there are three types of structures. So, one is a single layer feed-forward networks, another one is multi-layer feed-forward networks, the third one is recurrent networks. So in this session, we are going to learn about a single layer feed-forward network. We'll learn introduction about a single layer feed-forward network, and we'll see one example R function and perceptron binary classification model, neuron model, and a learning algorithm, how we will train that and how we will draw the linear separable and the limitations of a single layer feed-forward network, and we will see the advantages of multi-layer feed-forward networks. Okay, let's see the introduction part about single layer feed-forward networks. So the single layer feed-forward network consists of input layer and output layer. So it will take the data from input nodes and it will have some associated weights. With that weights, it will be added weighted sum up, and which will add some bias, and it will produce some output. So let's see the formal definition of single layer feed-forward network. A network without directed cycles facilitating information flow from inputs to outputs via weighted connections. So it will take a input and output, input layer and output layer. The input will flow from input to the output layer, and each input node will have the connection with the output node, each and every output node, and which associated with the weights. Okay, let's see the architecture. It consists of input and output layer. Here there is no hidden layer, only two layers. The single layer feed-forward network consists of. One is the input layer, another one is output layer. That's it. Next, node connections. How the each node will be connected. Each input node links to every output node which are associated with the weights. Next, how it will be calculated, the process, how the information will be processed. So to output node, the input is a weighted sum of input parameters, which will be from the input nodes. For example, x1. Then it will be connected with the output 1. Then there is a w1. Then this one x1 into w1 plus x2 into w2 and so on, which will be added to the output one. How many parameters coming from this output, all those inputs and weights will be sum up to this particular output node. Okay, we'll see in the next step. Next, how the activation decision will work means, if the weighted sum surpasses a threshold value. In the previous session, we have seen the activation functions, step function, ramp function, sigmoid function, and Gaussian function. Will take one of those functions and it will surpasses this output in V value. Already yesterday we have seen V equal to U plus B. So this V value will be passed if the threshold value is greater than or equal to, then that value will be 1. If it is less than, then it will be -1. And if it is greater than, then if it is 1, then the neuron fires adopting the activated value. Otherwise, it adopts the deactivated value. If this threshold value will be greater than, then the neuron will be fired and it will perform the particular task. Otherwise, it will be deactivated. Let's see the example. So here the example is, which will taken as two input nodes x1 and x2, the four output nodes O1, O2, O3, O4. The structure will be like this: x1 and x2 input layer and output layer O1, O2, O3, O4, and each and every output. So here the connections are x1 to each and every output node. There is a connection and there is a weight associated with okay, x1 to O1, x1 to O2, x1 to O3, x1 to O4. Each and every link will be associated with the weights in a similar way: x2 to O1, x2 to O2, x2 to O3, x2 to O4. In the same way, W21, W22, W23 and W24. The each and every link will be associated with the weights. This one, link weights denoted as a W, where I equal to 1, 2 and J equal to 1, 2, 3, 4. So the single layer feed forward network consists of input layer and output layer. So the inputs are, for example, X1 and X2, and output layer consists of 4 nodes, and each and every node will have the connection with each other, and that link is associated with the weight. Okay, let's see the binary classification model, that is perceptron. The formal definition is, when it is introduced, is a special form of single layer feed forward network pioneered by Rosenblatt in 1958. What is the purpose of this single layer feed forward network? Means to binary classification task, designed for binary classification task, dividing input into 2 predefined categories. For example, email filter means spam or not spam, 2 categories, or disease is present or not present, 2 categories. To perform binary classification, we'll use this single layer feed forward networks, and the purpose of this single layer feed forward network mainly is to draw the hyperplane, whether that draw the hyperplane or not. It will solve the only linear separable problems. Remember this one, the single layer feed forward network solve the linearly separable problems, which means it will draw the hyperplane in between 2 classes. For example, if you take zeros and ones, if it is draw the line to zeros separates and ones separate, then it is called as linearly separable. If it is not done, then it can't draw that lines like this, a straight line, then it is not a linearly separable. We'll see. Okay, so the architecture is a single output node. We'll see the next architecture. Activation function, here step function is used. Returns 1 if the weighted sum of input is greater than or equal to a defined threshold, greater or equal to. Otherwise, it returns -1. Okay, next let's see the perceptron model. Here, input nodes accepts input data for classification. Output node produce binary classification result based on the input and weights. Activation threshold determine the binary boundary for classification. So input values x1 to xm, weights w1 to wm, and there is a weighted sum sigma I equal to 1 to n, and which will be added the bias also, x1 xi wi plus b. Okay, this is the bias. Next, activation function. Whatever value induced field is there b, that will be passed to the activation function pi, and here we are taking step function. So it will take, if the threshold v is greater than or equal to threshold value, then it will be 1, otherwise it will be -1. Let's see the activation function. Step function used in this case is pi of v equal to, if v is less than particular threshold theta, then it is -1. If it is greater than or equal to particular threshold value theta, then it is +1. Okay, let's see the training a perceptron for binary classification. What is the objective? To determine the appropriate weights to classify. Training examples into 2 classes, C1 and C2. Linear separable. Draw the hyperplane. So here, if classes can be separated, for example, C1, C2, there is a hyperplane, then it is called as linearly separable. Let's see the definition. If classes can be separated by a hyperplane, they are linearly separable. If you can draw a straight line or a hyperplane in a higher dimensions to cleanly separate the data points of one class from another class, then the classes are said to be linearly separable. Let's see the training process. Adjust the weights. If it is not able to linearly separable, then what to do? training that weights. Adjust the weights to ensure correct classification. If the output is +1, then assign to a class C1, and if the output is -1, then assign to class C2. Let's see the differences between linear versus non-linear separable. Linear separable means a single straight line can separate classes on 2D graph. Examples are and, or, complement functions. Non-linear separable means cannot be separated by a single line, that is XOR function. Let's see the one example, OR function. So input is two binary values 1, 0, output +1 if either input is 1, -1 if both inputs are 0. Linear separability means can be separated by a straight line. Next, training is adjust weights to correctly classify input into C1 and C2. A training algorithm is used to train a perceptron which calculates the errors between calculated output and actual data and subsequently use this error to modify the weights. For example, expected output and actual output, there is a difference, then that is called as error. To adjust that error and to get the actual output, we need to adjust the weights, okay, to rectify that error. Let's see the OR function. Input value is x1 and x2. Output is x1 or x2. If both x1 and x2 are 0, then it is 0. Otherwise, all are 1s. Let's see the OR function graph is 2D graph. So 0, 0, okay, 0, 0, 0, 1, 1, 0, 1, 1. Output is 1, 1, 1, 0. Here, we can cleanly observe that the zeros and ones are separated with the hyperplane, a straight line. Then it is called as linearly separable. Okay, let's see the learning algorithm here. Initially, random weights are assigned to inputs, that is a range of -0.5 to +0.5. Later, the training data is presented to the perceptron and output is observed, whether it is expected output or not. If the output is incorrect, weights are adjusted using the following formula. Wi equal to Wi plus A into Xi into E. A is a learning rate. That learning rate is in between 0 to 1. And the learning rate is defined as if output is correct, actual and expected both are equal, then learning rate is 0. If it is too low, the output is too low, then A equal to some positive number. If output is too high, then A equal to some negative number. After modifying the weights, the next training data is applied using the updated weights and further adjustments are made if necessary. Once all training data has been used, the process restarts until all weights are correct and errors are 0. Then each iteration of this process is called epoch. So first, in this algorithm, it will say that first we need to initialize the weights with the range of -0.5 to +0.5. After that, we need to check the output after weighted sum up and weighted sum. After that, passing this weighted sum value to the activation function, there is an output. We need to observe that output. The actual output and expected output both are same, then it will be fine. If it is incorrect, then we need to check the error value and we need to adjust the weights to get the actual output and expected output both are same. To adjust the weights, the formula is Wi equal to Wi plus A into X into E. So Wi is the previous value, A is the learning rate. Already here we have defined how it will be taken, and X is the input of that particular node and E is the error value. Okay, after that, whatever modified weights are there, that modified weights are updated to the next training data, and again we'll follow the same process. Each and every iteration of this process is known as epoch, and we'll do the same to all the training examples until we'll get the stable values and let's see. Here, perceptron for OR function example. Initialize the weights, that is in between -0.5 to +0.5. So here W1 equal to minus 0.2 and W2 equal to 0.4. So consider the first training example A. First training data is x1 equal to 0, x2 equal to 0. The expected output is, if both are zeros, x1 or x2 equal to 0. Then compute the value y equal to step of W1 into x1 plus W2 into x2. So step of, what is the W1 value? Minus 0.2 into what is the x1 value? 0, plus what is the W2 value? 0.4 into what is the x2 value? 0. So minus 0.2 into 0 plus 0.4 into 0, step of 0. So which will get the output as y equal to 0. So compute y equal to step of W weighted sum equal to 0. The output is 0. Since y equal to 0, output is correct. That is what our function x1 and x2 output is 0, correct. And therefore no change in the weights are required. Next, consider another training data x1 equal to 0, x2 equal to 1 and output equal to 1. Let's again compute the same. Y equal to step of W1 minus 0.2 into x1 equal to 0 plus 0.4 into x2 value 1. Step of minus 0.20 0 plus 0.4 equal to 4 into 1 0.4. So which is step of 0.4 is equal to 1. So output equal to 1. Here actual output also 1. After computing is 1 and actual output is also 1. So after computing, the output is again correct. So the weights are not changed. No need to change the weights because expected output and actual output both are computed output both are same. Let's go to the next training data. x1 equal to 1 and x2 equal to 0. Output is 1. Then compute the step of weighted sum. Then the value is minus 0.2. Then the threshold value is less than. So the value is 0. The output value is 0. But the actual output is 1 and computed output is 0. Here there is a difference. So since y equal to 0 and desired output is 1, hence weights are to be changed. Here error is 1 equal to 1. Assume learning rate is some 0.2 for example. Updated weights are computed using Wi equal to Wi plus A into Xi into E is the formula. So first W1 equal to minus 0.2 plus A is 0.2, X is 1 into 1 equal to 0. Now W1 equal to 0. Again check for W2. W2 value is 0.4 plus 0.2 into 0 into 1 equal to 0.4. So now the new weights are W1 equal to 0, W2 equal to 0.4. Take these weights to the next training data. The next training values are x1 equal to 1, x2 equal to 1, output is 1. Now compute y equal to step of values. Substitute these weights into this formula. Then the output is 0.4. So the threshold value is greater than equal to 0.4. So the output is 1 and desired output is also 1. Both are same. The output is correct. So weights are not changed. So repeat the same process for all training examples with modified weights till obtain stable results to get all the output values, desired outputs and computed output values are equal. Okay. Let's see the limitations of perceptron. So here shortcoming, perceptron can only model linearly separable functions. It can solve the problems of linearly separable. Okay, what is the challenge in cases where classes are not linearly separable? A linear separator minimizing mean squared error is needed. An example is perceptron can't model XOR function due to a non-linear separability. So if you take XOR, we can't draw a straight line using the graph. So that is the one of the example of this. Why we can't use this XOR function, because we can't draw the straight line. So single layer will solve only problems of linearly separable. Let's see the advantages of multi-layer feed-forward network. Here, enhanced power, capable of handling non-linearly separable data, and which will have the multiple layers, input layer and two or more hidden layers and one output layer. Enable complex feature extraction and representation, contains more layers of neurons, nodes with nonlinear activation functions. And here we'll use the sigmoid function, facilitates nonlinear transformations, enhancing modal flexibility. These are the limitations of perceptron, and these are the advantages of multi-layer perceptron. In the next session, we'll see the multi-layer feed-forward network. Let's see the summary of this session. So we have seen when it is introduced, and what is the single layer feed forward network, how many layers contains, how it will process the information, and we have seen the example. So we have seen the training algorithm also, how to train the model, which will need to initialize the values, and we need to apply some formula to get the output, and we need to observe the error if it is any error is there. If error is there, we need to use the weighted new weight of we need to update the new weight value, find out the new weight value, and take that new weights to process the information, and we need to get again output. Again we need to observe the desired output and computed output. If it both are same, then no need to change the weights. If it is not, again we need to change the weights using the weight changed formula. Okay, this process will be repeated until we'll get the stable values, and each of these iteration is called as the epoch. And we have seen the limitations of single layer feed forward network and advantages of multi-layer feed forward network. Thank you.